Hello, I'm Ivan Vasconcelos. I'm an assistant professor of applied geoscience at Utrecht University in the Netherlands. Welcome to the third and final part of solving large-scale inverse problems in Python with PyLops. In this part, we're going to look at the Jupyter notebook called Radon. In this Jupyter notebook that you now see here, we're going to follow a few steps, and in these steps, we're going to fulfill the following objectives. Now, what you've seen from PyLops so far is what PyLops is, how to set it up, and you've now seen relatively straightforward examples on how to use the PyLops functionality to address problems in image processing. In this part, what we will address is how to do, firstly, how to take third-party software and make it into a PyLops operator. Secondly, we're going to look how to build more complex PyLops operators for specific problems. More importantly, we're going to look at how to use these made PyLops operators to solve optimization problems. Now, we're going to do that in the context of a specific inverse problem, and this is the problem of the inverse radon transform. The inverse radon transform is the problem that appears in computerized tomography or CT imaging or in MRI imaging. Therefore, it's one of the most well-known and studied imaging problems out there. Bear in mind that the things that we're going to show here are not state-of-the-art in CT or MRI imaging. The purpose of this tutorial is to get you familiarized as to how to build an operator from either scratch or using third-party software into a full inverse problem using PyLops optimization tools. We picked this example because it is a popular example, but bear in mind that there are more sophisticated tools for this problem if that's what you want to solve. Okay, so let's get started with our problem. To understand the problem of image reconstruction with the inverse radon transform, let's look at this cartoon here. Okay, so this cartoon demonstrates what is called the Fourier slice theorem. The Fourier slice theorem relates an image, which is what you see here as I, to the 2D Fourier spectrum of said image, K, through what are called parallel projections. Now, parallel projections here in this cartoon are demonstrated here by the blue arrows that show what would have been a shadow of the X-ray excitation as recorded along the line. So on this side of the image, you would have X-ray sources, and here you would record the X-ray transmission on the other side. Because some of the X-ray would have been scattered by, in this case, the body or some sort of target, you would see a loss in power in X-ray, and this is the projection, as we call it here. Now, if you take a projection over a line oriented as P, take its Fourier transform, here indicated in 2 by showing diagrammatically its Fourier components, and place them along a specific wave number that corresponds to the K direction, you can build, by taking successive progressions at directions P, the Fourier spectrum of this 2D image. And then by taking the inverse Fourier transform of the K spectrum, you can recover the image from the projections. This is called the 2D Fourier slice theorem. The main idea here is that we can relate an image to its projections. So now we're going to talk about how to build an image by using projection operators. To begin with, we're going to start by looking at a specific setup here for our projections. Okay, so this is a little recipe that you can follow to build projections. What I want you to pay attention here is that we have some options, right? If we have a set of projections P, so you can see here in this equation, as a function of an image and a projection operator P, we could simply invert that projection operator. If we have the Fourier transform and relate it to sampling, then we can look at the Fourier dual of that projection that's now in space K, And we could have the Fourier transform applied to the image and then sampled by a restriction operator R. Before we do any of this in PyLops, our starting point will be to say, well, is there a package out there that has something that we can use? Well, it turns out that scikit-image has a radon operator. So to start, we're going to look at the forward radon transform that comes from scikit-image, and we're going to look at an image reconstruction straight out of scikit-image using the so-called filtered back projection. So let's start at it. Remember, when you want to run this code, if you're running it in Colab, you'll have to run this first line here so you can install both PyLops and Scooby. In this case, we're in a local environment, so I'll just run the code. Here we're importing our libraries, which include PyLops, Scooby, scikit-image as our baseline. The very first thing we'll do is we'll import what's called the Shep Logan image. Okay, so I'll do this here. And here you can see a picture of the image. This is a 2D image that's often used as a common benchmark for CT, MRI, image reconstruction problems. So for that purpose, we're using it here for the same thing. This is the image that we start from. This is the image that we want to reconstruct. Okay, so let's start now with a scikit-image version of radon. You can see what's happening here in the codes. The first thing that we do is we choose a set of angles to which we get projections that's between 0 and 180 degrees at every 3 degrees. We call the radon transform directly from scikit-image, and that will produce a projection set to us. So if we evaluate this bit of code, here now you can see on the left-hand side the input image, the Shep Logan phantom, and its projections as generated by scikit-radon. Now, this picture shows you the intensity of the projection. This is what you see in the gray color as a function of space along some line at projection P. So these are pixels here. Think of them as just coordinates along the line that is slanted at a P. And the P slant is given by an angle. That's the projection angle that you see in the horizontal axis. Okay, so we know now that we have the radon transform, and that the radon transform outputs discrete projection values at locations along a line and for a specific angle. Can we make an image back from it? Well, scikit-image already has for us a functionality called iRadon. And iRadon can produce what is called the filtered back projection. Okay, this is not an inverse, this is a back projection, much like an adjoint would produce a back projection. So let's just run it and see what we get. Here we called the inverse radon with the option of the projection, and we get a picture back. And this is the picture, this is a reconstruction of our image coming from the scikit-image iRadon functionality. On the left-hand side, you see the reconstruction. On the right-hand side, you see the reconstruction error. For this picture and all other pictures here where we show a reconstruction error, notice that we're not showing the magnitudes of the reconstruction error. We leave it to you to find out how large these reconstruction errors are, but you can use the pictures as they're shown to appreciate the patterns in the reconstruction error. So now that we have what appears to be a forward operator, which produced our projections, and an inverse, which or a pseudo-inverse, a back projection here in the shape of the filtered back projection, can we build this into a PyLops operator? Okay, and the answer is yes. To do this, we're going to use a functionality of PyLops called the function operator. This is what you see highlighted right here. The function operator allows you to take Python functions and pass them as the forward and adjoint method to a function operator construct in PyLops, which returns a PyLops operator class that operates as the PyLops operators that you've seen in the last two parts. Here, the way we do this is to use the lambda functionality of Python to call both the radon and iRadon method functions of scikit-image and assign them to objects here, mvec and rmvec, which we then pass to function operators as the forward mvec and as the adjoint rmvec. The other two arguments here are just giving the dimensions of input and output for this PyLops operator. So if we run this, we just generated our operator, and now what we've done is we've effectively wrapped the radon and iradon functions from scikit-image into a PyLops operator. Now, this allows us to use the filtered free version of the back projection. Before we showed you a version of the filtered back projection. Now we can call iradon with no filter. This should represent what an adjoint is supposed to be, provided that that was the adjoint to the forward radon as called by scikit-image. So let's apply it and see what it looks like. You can see here that we're now using the FOP as we defined, right? This is the PyLops operator that is constructed from scikit-image's functions. And we will make a forward projection, and then we will make an adjoint projection here. So notice that right here, we're calling the adjoint method of the PyLops operator, which in turn points to the function iradon without filter. If we do this, we end up with this picture that you see here. So we take the input, which was the projected version of the image, using the PyLops operator, which is calling the radon function from scikit-image, and then taking that as the input for the adjoint reconstruction that you see on the right-hand side, give us the picture that we see here. If you scroll back for yourself and compare it to the previous image, you can see that this looks blurry. So clearly the filtered back projection is doing some sort of sharpening to the image. So we end up with the previous result that we saw. Now, the very important question, if you want to solve an inverse problem, is this an adjoint? Remember, that's a requirement for a PyLops operator. So we can always check whether a new PyLops operator truly verifies the dot product test, thereby saying that this is or isn't a true adjoint. We can do that very easily by calling the dot test function of PyLops. So this is what you see here, and we'll see what happens. Well, as you can see, iradon from scikit-image and radon do not form a forward and adjoint pair. What this means for us is that even though we wrapped it into a PyLops operator, we can't use these functions for solvers that require true adjoints. So what can we do now? Well, next, what we're going to do is we're going to leave aside our scikit-image functionality and just build one from scratch using PyLops. How are we going to do that? Okay, so the idea of building a radon transform using PyLops is actually very simple. In concept, the pseudocode for a forward projection operator is as stated here. For each angle theta, we rotate the image by that angle. And once it's rotated, we just need to sum or stack the values of that image over one of the axes. Now, what would the adjoint look like? The adjoint will take for each theta the adjoint of the sum operation, which would be a spread over a fixed axis, and then rotate it back to the angle theta at which it was rotated to begin with. That would be conceptually what the forward and adjoint operators would be. Now, how can we do this in PyLops? One way of doing this in PyLops, taking advantage of an already existing PyLops operator, is to recognize that a rotation in practice, numerically, all it needs is bilinear interpolation. In fact, it doesn't have to be bilinear, it can be any interpolation, but because bilinear interpolation is in PyLops, that's what we'll use. Now, we'll represent here the bilinear interpolation by the operator b for a fixed angle theta. And after applying the bilinear interpolation, we will just devise a sum operator here. And so for each angle theta, what we have to construct is an operator that has stacks of the bilinear interpolation that represents the rotation plus the sum at each angle theta, starting at theta 0 at the top, then moving for each theta sample down to your last theta sample. As a cartoon, you can see here how bilinear interpolation works. Right? You can think of a rotated image as just a interpolated version of your original image in black to the red values. This is why we're using bilinear interpolation. Notice that to ensure that the original image, here indicated with the dashed red part, fits after you rotate the image, one trick that we used all the way in the beginning of this code was to pad the image with zeros to extend its dimensions so that when we rotate it, it always fits within the interpolated grid. Okay, so let's illustrate this with a single image. Here we're taking our image and we're going to rotate it with a fixed angle. So we start with the image, we define the axes for the rotation via linear interpolation, so you can see the input and output axes defined here. Then we define a rotation operator as a simple change in coordinates. You can see here that the R, the rotation operator, is a well-known trigonometric change in coordinates. We recenter it to the axes, and then we plot. So let's see what this looks like. Here you can see a cartoon of it. You can see the coordinates overlaying on top of one another, and you can see the effect of the rotation is effectively to select a new set of coordinates that is interpolated to the points that correspond to a regular grid on a rotated axis. Okay, so now this means that we can build a PyLops operator off of it. So what we do is we take our rotation operator here, and we use it as a basis for the bilinear interpolation. This allows us to simply define a PyLops operator by calling the bilinear interpolation from the signal processing toolbox within PyLops. Therefore, to rotate the image itself, all we need to do is to now apply this PyLops operator to the image, and it should simply rotate the image by applying bilinear interpolation. So let's see if that's what happens. Here you go. We now call the PyLops operator ROP, and it applies bilinear interpolation in order to effectively rotate the image. So you see the input image on the left-hand side, the rotated image on the right-hand side. Here you can also see the effect of the dimension extension, or the zero padding, where you see that the original image has larger dimensions than the rotated image. That's to ensure that the image we want to rotate fits within the output image at all theta angles. Okay, so this is a rotation for one angle. Now let's make an operator that can apply this n times and make the sum the projection for all the angles. In order to do this, we're going to define a new operator here. It will take the original grid, create a new grid off of it, convert the angles to radians. Then we make this empty array that's going to house all of the appended arrays, all of the appended operators for each one of the thetas, which is what you see here. Now we loop over thetas, create the R, change in coordinates. That gives us the data that we can interpolate. And then we can create a appended PyLops operator for each one of this, which contains the bilinear interpolation that you see here by calling the bilinear operator from the signal processing toolbox of PyLops, and then the sum operator applying next to it. So this is the SB operator that we saw in our definition above. So we can now evaluate this. This creates now our full radon transform operator for all angles of theta by producing a bilinear interpolation at each theta that corresponds to the rotation, followed by the sum over the fast memory access direction here, which you can see here by 0. Okay? Okay, so now we've created an operator. Let's see how it works. So now we'll take our operator here. We make an object that actually contains the operator. You can see there that it's already showing us for the dimensions and rotations that we want, what the dimensions of that operator is. Then we can apply it as a forward pass here. And then we can see what the projections look like compared to the projections that we created before using the radon from scikit image. So you see here on the left, you see the PyLops forward radon. In the middle, you see the scikit image radon. And then you see their absolute difference. Notice that the difference is larger at the edges. That's because in the Shep-Logan phantom, the edge, the white edge that's around the picture has the largest numbers, and therefore that's where you see the largest differences for the bilinear interpolation errors, which is effectively the difference that you see in these two projections. In any case, this is a good forward operator because you can see it comes really close to a third-party projection operator, thus giving us some confidence that we've created a suitable projection operator. The difference, though, between the projection operator that we just created and that of scikit-image is that the one we just created has a well-defined adjoint because we created it from PyLops operators that already had well-defined adjoints. So we're using the advantage that when you compound PyLops operators with well-defined adjoints, the adjoint of that compound operator is already well-defined by itself. A consequence of this is that we can directly use our PyLops operator now to estimate inverses to our problem. So let's see if we can use this for inversion. To do this, we're going to show you two examples of inverse problems. This is for the same problem we have here. We have two options. The first option, the one that you see on the top here, is called L2 regularized inversion. So in this case, we're going to try to solve a least squares problem with a constraint for smoothness. So this term that you see here is weighing the weight of the Laplacian applied to the image. So this is a smoothing operator against the least squares norm of the misfit between the produced projection and that is observed. Now, the second option that we see here is going to solve us technically an L1 problem, where what we're trying to do is minimize the L1 norm of the derivatives, the first order derivatives of the image in two directions, the x and y directions, while using the least squares norm as a constraint. Okay, this is called the TV regularized inversion problem, and we'll see how we solve it here in a minute. Let's start with the top one, the L2 regularized inversion. Okay, so in order to do this, we're going to call directly or least squares inversion from the PyLops library. In order to do this, we need to provide the regularization operator, and by that we can call the Laplacian that's already in PyLops. And we'll pass our built PyLops operator that has the bilinear interpolation and the sums for the projection operator, the Laplacian that we just create here, and then we'll call our iterative regularized inversion solver. Okay, so we'll do that here. Now this will take longer than a filter back projection did, as you can see here, because each iteration of this solver needs to call one adjoint pass of the operator and the forward pass of the operator. So each one of these iterations already costs twice as much as a filter back projection in principle would cost. Now, the way we set up our inversion here is it will stop when it reaches a tolerance for the least squares norm or when it reaches 20 iterations. Now, you can see here that it stopped at 20 iterations because it didn't quite reach the tolerance level that we predicted or asked for. And then we'll see what the result is. Well, on the left-hand side, you can see a pretty good reconstruction of the image. Now, this reconstruction looks smooth, and it looks smooth because we explicitly used a smoothness constraint by using the Laplacian operator as a regularizer. On the right-hand side, you can see that the pattern of the errors of the reconstruction looks different than that of the filter back projection that we saw before. This is expected, of course, because the constraints we just used to solve the problem were not even present when we looked at the filter back projection. Now, what happens if we use a different solver? Let's look at the second problem that we looked at, and that was the problem of the TV total variation regularization. Now, for the total variation, we're going to use what's called a split Bregman solver. A split Bregman solver is designed to solve an L1 optimization problem subject to the least squares norm. In this case, because we want the total variation problem, the L1 optimization problem corresponds to maximizing to minimizing the norm of the one norm derivative, first order derivatives of the image in both x and y directions. So in order to do that, the first thing that we do here in our code is create a PyLops operator that incorporates the directional derivatives in the x and y direction, first order directional derivatives. Here we can call the first derivative operators also from the PyLops library. Once we built this, then we can solve the problem by calling our solver from the optimization library of PyLops, now the sparsity promoting library where L1 solvers are, and the split Bregman solver, which is what you see here. As an input, we're passing our operator, and we're now passing the operator that we created for the first order derivatives. Then everything else is quite similar. We give it the data, and we specify either a maximum number of iterations or a tolerance level. Much like the least squares approach, you will see that this takes longer, much longer than a filtered back projection, and that's because each iteration of the split Bregman solver needs to call the forward and adjoint operations in this case, thus taking longer. Now, the split Bregman solver also has additional norms that it needs to compute per iteration, which makes it more expensive than the least square solution. So we'll have to sit here and wait until it either reaches the minimum tolerance that we want or 20 iterations. So here's a third iteration. Okay, now that we've waited a bit until we reached our total number of iterations, in this case, you can see it stopped at 5 iterations, we can see that what the result is. Notice that the TV regularized result gives us a fairly good image reconstruction. Of course, it took a lot longer because of the reasons I mentioned before. You can also see the error here in the pattern of the error, again, looking different than previous error patterns that we saw. If you'd like for yourself to quantify and plot these errors relative to one another with a specific fixed scale, feel free to do that. Now, we can visualize at last all our reconstructions together. So for that, we have our very last box. Here we have all of our results, starting with the original image on the left-hand side and a little zoom of it underneath on the second column. Then we see the filtered back projection from scikit image. And then from the PyLops operators that we created, we see the result of the least squares inversion and of the TV regularization. TV regularization in this case is far superior than the other two because this original image is sharp. And so using the sparsity promoting split Bregman solver with a TV constraint gave us the best results in this case. And of course, both inversions look slightly better than the filtered back projection because of the ability of imposing constraints and using well-established solvers. This is precisely what we want you to learn and take away from PyLops, and to give you an idea of how easy it is to construct an operator and use some of the state-of-the-art solvers that we have here. I hope that you've enjoyed this exercise. We left a few things for you to work on towards the end of this notebook, and we hope you'll enjoy, and we're available for you for any discussions or anything else you would like to discuss. Thank you, and see you around.